All right, we're going to take a look at binomial theorem and binomial probability. Some of you may have heard of Pascal's triangle, which is off to the right here. You can see the outsides are all one, and then there's a unique pattern to the triangle itself, and it's actually based on combinations. We talked about combinations a couple days ago, but looking at the outcome, 0, choose 0, 1, choose 0, blah, 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 blah. Those are the actual values they work out to be. The nice thing about this is we can use this as a shortcut with polynomial expansion. All right. If you think back to, chapter 5 when we were working with polynomials, if we had you expand x plus 1 to the third, you would have to take x plus 1 times x plus 1 times x plus 1. And then what you'd have to do is take two of them, FOIL them out, and you get x squared plus 2x plus 1. Then when we distribute again, we get x cubed plus 2x squared plus x. Then we distribute the 1 plus x squared plus 2x plus 1, which simplifies to x cubed plus 3x squared plus 3x plus 1. It's not a coincidence, but if we look at our coefficients in this expansion, they correspond directly to values in Pascal's triangle. And that's what the binomial theorem, you guys, is kind of based on, is this idea that we can shorten up the process, okay? I'm going to advise you to not look at the technical definition, because when you look at this, most of you think that probably looks like vomit on the page. That means nothing to you, okay? But we're going to show you how this can be used and simplified down. I'm going to walk you through the first one so you can see, and then we'll start expanding on examples from there. So if I want to expand x plus 2 to the fourth, the first thing I usually do is take the first value in the expression, and I start at the power of the expression. So I do x to the fourth, then I leave some space and I do x to the third, x to the second, x to the first, and x to the 0. So you start at the power and work your way down. Then, for the second part of each expression, you start with the second term and start counting up from 0. So you have 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. And then your last step in using the shortcut is the combinations. So we always start with n being your power. So we have 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. At that stage, all it is math to simplify things down. So 4 choose 1, or 4 choose 0 is 1. X to the fourth, 2 to the 0 is 1. 4 choose 1 is 4. X cubed times 2. Plus 4 choose 2 is 6. X squared times 4. 4 choose 3 is 4 times x times 8. 2 to the third is 8. Plus 4 choose 4 is 1. X to the 0 is 1. And 2 to the fourth is 16. And if we simplify that down, we wind up with our expanded expression. Again, we could have done old school and taken x plus 2 times x plus 2 times x plus 2 times x plus 2 and FOILed all of that out, but we would eventually get to the same spot. The binomial theorem, usually with squaring and cubing things, probably not much of a shortcut, But when we have fourth, fifth, sixth power we're asking you to expand expressions on, the binomial theorem is going to be a shortcut for you. Okay? So let's dive into the next one here. We have 2x minus 3. So like I said before, I usually like to start with the powers. So I'm going to start with 2x to the fourth. And then I'm going to have 2x to the third. And I have 2x squared. And then I'm going to have 2x to the first. And then I'm going to have 2x to the 0. Then I dive into the second part. So negative 3 to the 0, negative 3 to the first, negative 3 to the second, negative 3 to the third, negative 3 to the fourth. Okay, so that's kind of the basic part. And then we want to put the combinations in front. So we wind up with 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, and then finally 4 choose 4. Sorry, it's getting a little crammed down there. More legible notes are available online if you need. Then from there, we wind up just simplifying things down. So we have 4 choose 1, 2 to the fourth, 16x to the fourth, negative 3 to the 0 is 1, 4 choose 1 is 4, 2x to the third is going to be 8x cubed times negative 3. Negative 3 to the first is just negative 3. 4 choose 2 is 6. 2x squared is going to be 4x squared times negative 3 squared is 9 plus 4 choose 3 is 4 times 2x times 3 cubed, which is negative 27. And then our final expression, 4 choose 4 is 1, 2x to the 0 is 1, and negative 3 to the fourth is 81. So we combine all those together. We wind up with 16x to the fourth minus 96x to the third plus 216x squared minus 216x plus 81 is your expanded polynomial of 2x minus 3 to the fourth. Again, some of you right now are probably like, why the heck didn't I just do 2x minus 3 and multiply it out 4 times? That's great. But like I said, with larger expansions, degrees, 4, 5, 6, binomial theorem is actually going to be a shortcut. When we, if we were doing IQs, we would have you do, I believe, a degree 6 expansion if we gave you a test. We have a degree 5 expansion where, it's going to take you some time to multiply those expressions out. So the expectation is you know how to use the binomial theorem to your advantage. All right? Continuing on, finding specific terms using the binomial theorem is actually pretty straightforward as well, especially if you kind of have a good understanding of things. When we're looking at the third term of this expression, 3x minus 5 to the 12th, what we want to do is we want to think about counting. So we started with, not 4 choose, but 12 choose 0 would be our first term. 12 choose 1 would be our second term. 12 choose 2 is going to be the third term of our expression. And that's what we have here. Keep in mind, we take our 3x, right? And we start at 12, and then our second term goes to 11, then our third term goes to 10. Then we're looking at the negative 5 piece. Remember, negative 5 starts at 0, and we count up. So the first term is going to be to the 0, then to the first, then to the second. A good trick on these is always making sure your exponents add up to the final exponent. Keep in mind when you do that, the R value of your combination should match the exponent of the second. So we have 12 choose 2, negative 5 to the second. Those should match. From there, we just want to use our calculator to figure things out, or you can expand it by hand. 12 choose 2 is 66. 3 to the 10th is 59,049. We have x to the 10th, and then negative 5 squared is 25. So we wind up with 9743085. So 97,430,850 x to the 10th. Using that same mentality, if we wanted to figure out the 9th term, well, keep in mind we started at 0. So our combination is going to be 1 less than the term we're looking for. Like in part A, we have 12 choose 2. We're looking for the 3rd term. So 12 choose 8 would be the coefficient of the 9th term. Keep in mind, like we said before, the power of the second piece is always going to match the R value in your combination. Then your exponents should always add up to 12. So that's how you kind of construct the specific part of your binomial expansion. Then, like I said before, it's just filling in these values, using your calculator to come up with them. And then we multiply the 3 numbers together, and we wind up with 15,662,109,375 times x to the 4th is the 9th term of that expansion. I will never have you do a degree 12 expansion fully, just so you know. I don't hate you guys that much. All right. The last thing, using the binomial theorem again. So those were more kind of step-by-step walkthrough. We're doing the same mentality here. So if I'm looking for those numbers, so I'm looking for the coefficient of the x to the 4th term. So keep in mind, x to the 4th. So I'm going to start at 10 and work my way down to 4, correct? So I know it's going to be something 2x to the 4th, which means 1 needs to be to the 6th, okay? Remember, our exponents always have to add up to the overall power. Then from here, if you remember before, the exponent of the second half always matches the R value in my combination. So then what I have to do is figure out what 10 choose 6 is and multiply it by 2 to the 4th, which is 16, times 1, and I wind up with 3,360. Okay. Same mentality here. I'm looking for the x to the 8th, so I know that 3x is going to be raised to the 8th power, which means negative 2 must be to the 4th, because those two exponents have to add to the total, which is 12. Then we know the exponent always matches the value of my combination. So we have 12 choose 4, 3 to the 8th, and negative 2 to the 4th. And you wind up with 51,963,120 is the coefficient of the x to the 8th term. Okay. Keep in mind, when it asks for just the coefficient, we just need the number. We don't need the actual term of the expression. The last thing you guys were looking at is binomial probability. Keep in mind the formulas here. We'll show you how to use it, and they'll probably make more sense. So we'll just dive right into example 4. There's always some key things you want to look for. So 15% of Jenny's calls end up in a sale. If she makes 20 calls in a given hour, what's the probability she closes on 5 deals? Okay. So some of this to keep in mind. P is the probability of success. So when we're trying to figure out our probability based on this event, please keep in mind binomial probabilities are kind of a yes or no. It's not a scaling probability. It rains or it doesn't. She makes a sale or she doesn't. You get the question right or you get the question wrong. So in these events, the probability of success is 15%, and we're looking at 5 calls. So the chance she gets 5 calls or 5 sales in 5 calls is 0.15 to the 5th. Keep in mind with binomial probabilities, if she makes a sale, that's 15%, the chance she doesn't make a sale is 85%. If she's making 20 calls and she makes 5 sales, she has to have 15 calls that she doesn't complete a sale on. And that's where the P and Q part of your binomial expression come from. So it's your number of successes and your number of your failures. Keep in mind, thinking back to permutations and combinations, the order doesn't matter. So she can make 5 sales and then screw up the next 15 times. She could, spend 15 calls working into her, whatever, sales pitch and then close the deal on the last 5. Since order doesn't matter, that's where the combination piece comes into play when we're figuring out binomial probabilities. Okay? The order of those 5 sales doesn't matter in those 20 calls, so we're always going to multiply by that combination out front. You can use your calculators to figure that out, but then we do 20 choose 5 times 0.15 to the 5th times 0.85 to the 15th. Again, that can all be typed in as a single string in your calculator, and you'll get 0.103 or 10.3%. So the chance of success is P. The chance of failure is always going to be 1 minus P. Those should add up to 1. N is your number of trials, and X is your number of successes. All right, so looking at the next problem, Mike's taking a true-false quiz. We're looking for at least 3 correct. So that means 3, 4, or 5 correct on the quiz. So on this one, we actually have to do 3 different binomial probabilities and add them together. So we have 3, we have 4, and we have he gets all 5 correct. Well, if it's a true-false quiz, the chance he gets 3 correct is 1/2 to the 3rd. If he gets 3 right, he has to get 2 wrong. Looking at the situation where he gets 4 correct, that'd be 1/2 to the 4th. If he gets 4 correct, he has to get 1 wrong. And then finally, we have 1/2 to the 5th and 1/2 to the 0. Again, our powers add up to 1. When you actually figure out each of those events separately and add them together, you do get 50%. All right, so the chances he gets at least 3 out of 5 on at least 3 correct on a 5-question test is 50%. All right. Looking at this last situation, Mike needs 1 more point for an A this quarter. What's the probability he scores at least a 1 out of 10 on the final test? So keep in mind, this is looking at 1, 2, 3, 4, 5, 6, 7, 8, 9, or all 10 correct. So in this instance, we could add all those events together, which is going to be a lot of calculations, or I can figure out 0, probability of 0, and subtract from 1. That's going to be a lot easier because then I only have to do 1 calculation, the probability of something essentially not happening, and subtract from 1. So we have 1 minus, well, we're trying to figure out the combination or probability that he gets 0 correct. So 10 choose 0. It's multiple choice still. So we want 0 successes and we want 10 failures. So this right here, 10 choose 0 times 1/2 to the 0 times 1/2 to the 10th is the probability he gets nothing correct, which means 1 minus that is 0.999, or 99.9% chance. That's binomial probabilities. They are again related back to that binomial theorem. Let me know if you have any questions.